All right, so we're going to go into example 1 for sets. And before we get into anything else, let's remember a set is a unique, unordered list. So it's unordered. So ABC is the same as the set of BCA. And they're unique. So A, B, B, C, B is exactly the same as the other two. So these three sets up at the top, those are all equivalent. Let's keep that in mind as we go through this example. I'm going to call this one set S1. I'm going to call this one S2 and call this one S3. And I'm going to create a new set. We're going to call this set T. And we're going to say that T equals A and B. All right? Another important piece of notation that we use with sets is exists within. So if I say X exists within T, what that means is that X is some member of T. X could be A, X could be B, it could be something, well, it can't be anything else in the case of T, but it has to be some member of T. If I say T is a subset of S1, what that means is for every X that exists in T, then X must also exist, be a member of S1. That is what this means. And this then symbol is really implication. Depending on kind of which chapters you've done in which order, you might not have seen implication yet, but that comes up a lot when we talk about predicate logic and propositional logic. So if X exists inside T, then X exists inside S1. That's what we mean when we say T is a subset of S1. Right? And it's true, right? A, we should be able to, shouldn't have to draw this here, but A exists in S1 and B exists within S1. Now you could not say that S1 is a subset of T because C does not exist inside T. So the converse is not true. But T is a subset of S1. All right, so knowing that, let's take another look at our claim that S1 equals S2 equals S3. Let's start with S1 and S2. If they're equal, that would mean that S1 is a subset of S2 and S2 is a subset of S1, right? That is, every member of S1 is also a member of S2 and every member of S2 is also a member of S1. If both of those are true, that means they are equal. And since A is a member of S1 and S2, B, C, that's obviously true, right? By the same token, if we have S1 must be a subset of S3, and S3 must be a subset of S1. Well, let's take this first claim here. Is A from S1 a member of S3? Yes. Is B from S1 a member of S3? Yes. Is C from S1 a member of S3? Yes. So that is true. Conversely, is A from S3 a member of S1? Yes. Is B? Yes. Now there's a copy of B, but it's still true. There's C, true, and another B, but again it's still true. So our second claim is true as well. And since S1 and S2 are equal, then if S1 is equal to S3, then S3 must be equal to S2. Does that make sense? So that's how, using the definition of a subset, we're able to prove that order doesn't matter and repetition doesn't matter when we're talking about sets. Okay. Now there is one area where the uniqueness of a set does become important, and that's when we talk about, remember, the cardinality, right? That's what those bars on each side mean. And that means the number of unique symbols. So cardinality is a very important concept, and if two sets are equal, they must have equal cardinality, right? That makes sense, I hope. Okay. Some sets are bigger than 3 values and cannot be expressed within curly brackets by writing each one. For example, real numbers, 1.000000 infinity. So obviously, that is not a good choice for us to represent using the notation that we've been using. So how do we represent those sets? We still use the curly bracket, so it's clear that we're talking about the symbols within a set. And then our notation, if it's, for example, real numbers, it'll look something like x such that x exists within our set of real numbers, and whatever conditions we put on it, x greater than 1. Right, or greater than or equal to, or whatever our conditions are. Often we kind of shorthand it to say x such that x is greater than 1. If we're doing a bunch of problems and they're all within the set of real numbers, we can do that. I think it's clear if you write the whole thing out. Sometimes the bar is not used, and instead kind of the colon is used as a shorthand. They all mean the same thing, right? X such that x is a real number and it's greater than 1. Finally, let's talk about intersection and union, which are very important set concepts that come up a lot and are really most easily described with a Venn diagram. Okay, so here we have two sets, A and B. Our intersection is this area here where both A and B overlap. Our union includes all of set A, all of set B, and the intersection. And we write that in our set notation. We say A union B to indicate all of this. Right, everything in set A, everything in set B, and everything that's in both of them. And we indicate intersection with that symbol, right, which is just this area that is both in set A and in set B. Okay, that being said, what do we mean if I was to say not A union B? That means everything that is not in set A, not in set B, and not in their intersection, which basically means everything else. Remember, in the last video we talked about that universal set that everything is a subset of, right? So when we talk about not A union B, we mean everything that's in the universal set, everything else except for A and B. We often talk about the differences between sets, right? So A minus B would be everything that's in set A except for that is not in set B. To indicate it visually, the red area is A minus B. And then conversely, B minus A is going to be what is now the yellow area. Now, going back to our set notation, let's talk about, all right, so let's go back to A union B. What do we mean is x such that x exists in A or x exists in B, right? Which makes sense. A intersection B, I'm going to move down a little bit, x such that x exists in A and x exists in B, right? Which makes sense. The intersection is in both A and B. The union is in either A or B. All right. So those are taking the set theory and going back to the Boolean and functions and propositional logic we're covering elsewhere in this course. Make sense? If that's not clear, don't worry. When we get to example 1, we're going to dive back into Venn diagrams, and we'll do it with some concrete sets, and I think this will start to make more sense.